with various classes of groups. What time do I stop? Okay. And we start drawing a picture of the various classes of groups. I've defined probable groups. Okay, and then I sort of had this stronger class of maybe it matters if I have probable groups where I require them to be quasi-geodesics. Now, and then there's this other class which might be smaller where I require this stronger condition of bicombability. And then maybe it matters whether I do that with quasi-geodesics. And this is what we call the semi-hyperbolic groups. Okay, so this is bicomb with quasi-geodesics. And just pulling back, it's just a little lemma, but pulling back, this contains the cat zero groups. It also contains the hyperbolic groups. Now remember that the hyperbolic groups, we don't know if hyperbolic groups are cat zero, but this is a place where they'll definitely have this geometry. Now, and these guys, obviously this is the two-sided version, right? So those guys obviously sit in the side. Now there's other things I might do. Now there's weaker things that I might weaken the definition here. And there's various weakenings, and I want to just state two of them. Like there are lots of definitions, and you can stare at these things yourself and think about weakening the geometry. So how might you weaken the geometry and keep the theorems? Well, we don't have any theorems yet, so we have to start proving some theorems in a minute. Okay. So further weakenings. So first of all is what turns out to be a very interesting one. Brings in a lot more groups. Asynchronous cones. So this is where you keep the picture, right? So you keep the picture that you want this sort of weak convexity. So you keep the fact that if this is, that if things are going to end the distance d apart, right, then all the way along it's never more than kd apart. You keep that picture, but you don't require your two fellow travelers to go along at the same speed here. Okay? You're allowed to go along at speed 2 here and speed 1 here, for example. Okay? So given the endpoints gamma and gamma prime, you're allowed to change the monotone reparameterization of the common lines. Okay? So I want to say that you allow monotone reparameterization. I'm not very much definition so carefully, but I hope that's clear, right? So you keep the picture, but you don't have to go along at constant speed here. You're allowed to vary the speed you go. And so that will give you some weaker notion that's called asynchronous cone. And there's all sorts of other things to go on here. You might think that this is all getting a bit silly, but let me show you something that I find really remarkable that that shows that any constraint on the geometry of a cone will tell you. So I'm going to state a result that says, well, I'll give you the slogan and then I'll give you the precise term. So the slogan is any constraint on cones with non-trivial classes. By which I mean it's not all groups. As soon as you put any constraint at all on the geometry of a normal form, you'll find you excluding some groups. So let me make an easy remark. Okay. So you've got gamma, any finitely generated group, absolutely any finitely generated group, and just sigma gamma, choose a normal form, there's absolutely any choice of geodesic. Absolutely anything. Right? So that can be completely stupid. Right? It can be the combing lines might have nothing at all to do with each other. So there's combing lines that join, that end at distance 1 apart, say, and they might just be like that. It might be a big fat, almost like circle. Okay? So let's suppose, so these are 2 points which are distance 1 apart, and let's suppose that they're both in the ball radius m about identity. Okay, well, how far apart might I get when I go along these geodesics? Well, before I get to halfway, the fastest way to get from there to there is just, oh, forget it, I'll go back to the origin and then go and give him his keys, right? So that's less than n over 2 and less than n over 2, so it's less than n. Okay? Once you're past halfway, well, you might as well go to the other end. Okay? So the maximum of the distance between gamma t and gamma prime going to gamma prime at t. Is it n or n plus 1? I think it's n. Maybe it's n plus 1. It might get, no, maybe it's n. It's a circle of odd length and it's inches. I think it's n, so it's something like that. Because you go to before you're halfway, you just go back to the origin. Once you're past halfway, you go to the end, but then it costs you 1 to go across the bridge, but you were past halfway, and it's an odd distance. I think that's right. I might be out by a plus or minus 1 here, but it doesn't affect the moral of the story. Okay. So that is no constraint on a group. Right? If I said I have a combing of the group with this property, then it's no constraint on the group. Right? Here's a theorem. So, right here. Let me just modify that by a tiny amount. So if gamma has any combing, now I'm not requiring it to be a geodesic combing or anything anymore. It doesn't have any sort of other properties. So that for all n sufficiently large, and if I take gamma and gamma prime with all radius n, which are distance 1 apart, like there, they're neighbours. But let's suppose that the maximum, that we just tighten it a little bit. So just for sufficiently large n, the furthest apart they get is, now you might think I'm about to write root n or something dramatic like that. I'm not. I'm just going to require it to be less than n minus 1 for sufficiently large n. So just take one little step. Surely that can't matter, right, in the grand scheme of things. This is enough to imply that gamma is finitely presented as a solvable word problem. And in fact, the Dane function, which I was talking about yesterday, which measures the complexity of the word problem, Brian was talking about my parametric function earlier, it can be at most e to the nth u. So as soon as you put any non-trivial constraint on the geometry of combing at all, you constrain the groups to a remarkable extent. And it's easy to write down groups that don't have these properties. So that tells you that when you're defining these groups by constraining the sort of geometry of normal forms, you're immediately throwing away loads of things, even when you put tiny constraints. So when you put these more serious constraints that sort of look like non-positive curvature, you expect to get a lot. So even with very weak constraints, you'll get interesting theorems, like this one. As you put more constraints, you'll get more theorems. Okay? Now, I haven't got back to these languages, so let's get back to these languages. So here is what I keep saying I'm going to talk about, automatic groups. And here is the theory of bi-automatic groups. Okay, so that's the two-sided condition, that's the one-sided condition. Okay, so what I'm going to do, as you might guess, is combine the linguistic constraints with the geometry. Okay? Because we know in the case of hyperbolic groups that we have this wonderful fact that you can recognize the geodesics as a regular language, and you get the nice geometry. So in fact, the hyperbolic groups are going to go there. So the definition, this is Epstein et al. Restart this by Cameron first. Epstein's the main author of the book. But gamma is automatic. We put bi-automatic here. If it has a normal form, a combing, so generators, taking our section, our normal form, so that two things now, we have the language of normal forms is a regular language, the simplest type of normal, simplest type of formal language. And secondly, we have the two-sided fellow have a fellow traveler property. Which is that one. That's for automatic. And for bi-automatic, you get the two-sided fellow traveler property. Which is, it's gone. It's that one. Okay. So that's what you do. You combine the natural convexity condition that you get from non-positive curvature with the regularity condition that arose in the condition of geodesics and hyperbolic space. Now, you might think he's forgotten to say that the combing lines are quasi-geodesics. Because that's part of this. That was the tightening when I said it follows for free because the language is regular. Okay, so when you put these linguistic constraints in the language, it will also give you hidden geometric constraints. So just having that geometry, without saying how long the lines are, if the language of normal forms is regular, it will automatically force the combing lines to be quasi-geodesics. You can prove a lot more about automatic groups than you can prove without the regular structure. But it's hard to find examples that distinguish between all of these classes. Okay? So for a long time, nobody knew if any of these classes here were distinct. Okay? But they are. Okay? So it turns out that these are not equal. Those are not equal. What else do we know? Some of them horribly we don't, but that's definitely not equal. That's not equal. How do I know that's not equal? Because there, so mapping class groups are automatic and semi-hyperbolic. So they're not cat zero groups, but they sort of have the coarse equivalence and they have the right regular structure for it. Okay? That's mostly due to motion. The hard bit's due to motion. Hammond step has a different proof. The motion goes to this one. You get a lot more groups by this classification. Okay? I'm struggling with the fact that I'm out of time. I want to give you theorems and examples. We'll have a 2-second poll. Who wants theorems? Who wants examples? Theorems? Examples? Oh, right, okay. I'll say the theorems and write the examples. Right. Theorems. So here, you've got a solvable conjugacy problem. Here, you've got a solvable word problem and quadratic isoperimetric inequality. quadratic or linear Dane functions. The reason you can tell that some of these classes are different is because up here you get examples with unsolvable conjugacy problem, whereas here you can prove you get a solvable conjugacy problem. Here you can also prove that the isomorphism problem is undecidable. So remember I said we very much would like to know. Here you can decide isomorphism. Here we don't know if you can. By the time you're up here, you definitely can't. Okay, so if you weaken the definition of non-positive curvature a bit, you get classes of groups with an undecidable isomorphism problem. In all of these classes, you get groups that are finitely presented and type FT and finite classifying spaces. Well, that's not quite true. Finite skeleton and FT dimensions for the classifying spaces. All the way up to the biggest class of countable groups. That is actually quite tricky. You think it's easy when you first look at it, and the obvious proof fails. And so it's quite tricky. There's various algorithmic properties I've also missed out. A very important property of semi-hyperbolic groups is that you can prove that translation numbers, remember these translation numbers of elements, they're always positive in semi-hyperbolic groups. And from that, you can deduce that all cyclic subgroups are quasi-symmetrically embedded, like geodesics in a cat-zero space. You can deduce that all finitely generated abelian groups are quasi-isometrically embedded. Okay, so they all come with some sort of quasi-form of the flat torus theorem. You can't, unfortunately, we don't know if you can control solvable subgroups, which was one of the things about cat-zero groups that really relied on the cat-zero local structure. We don't know if semi-hyperbolic groups can have solvable subgroups that aren't virtually even. Okay, I realise that I'm out of time, so I'll put down the chalk and pretend to stop and carry on. You asked for examples. Well, what examples? So out of Fn is not in this picture, Ollie. You don't quite understand that. Out of Fn has exponential isoparametric inequalities, and that is sort of ruled out by this. Okay, so out of Fn, which appears in this structure, which is captured by asymmetrically hyperbolic group theory, is not captured by this sort of semi-hyperbolic group theory. And it's a really stark difference between the mapping class group and out of Fn. Okay, mapping class group is here, out of Fn isn't. For lattices, things like SLNZ, non-uniform lattices in higher rank are not in this picture. Okay, that's a hard fact, but it's true. Uniform lattices, co-compact lattices in semi-simple groups are in this picture. They're already here as cat-zero groups. Mapping class groups are here. Lots of central extensions. If you take an arbitrary central extension of a hyperbolic group, that will be biautomatic. That's the theorem of Neumann and Reeves. So all of these sort of twisted products, like the unit tangent bundle of hyperbolic circles, they're not captured by classical non-positive curvature, but they are biautomatic. They all appear here. So you get lots of examples. You get lots of sort of twists on classical examples. And finally, let me say about three manifolds, which we all know and love. Let me say the theorem, I'll write it down if you ask me to. Epstein and Thurston proved, so you'd like to say that all three manifold groups appear here, and they do, but it's quite subtle. Epstein and Thurston proved that if you take a compact three manifold, then usually the fundamental group is automatic or even biautomatic. So you get both the algorithmic structure and the geometry. But that's provided that the manifold can't be written as a connected sum where this is a nil or a solved piece. Okay, and a nil or a solved piece is basically a torus bundle over the circle. Okay, so you'll have a fundamental group with that sort. If your three manifolds are torus bundle over the circle, it will not appear down here as a biautomatic group. But later I proved you can get these comings, or slightly asynchronous comings, that I was going to explain to you. And what's really in this paper, myself and Gilman, is that if you allow indexed languages instead of regular languages, then you get all three manifold groups. Okay, so that's why You've got a hint of that already with these Euclidean lines, but in fact, if you include index languages as well as regular languages, within this sort of semi-hyperbolic group theory, you can include all three manifold groups. Okay, so I'll stop there. Also said, like, this theorem of Niblo and, everyone's talking about cubes these days, Niblo and Reeves, which is refined by Jacek-Strijkowski, is a very nice proof that any group that acts properly and co-compactly on a cat-zero cube complex is biautomatic, so it's the best class. Questions?
Yeah, in those examples of Niblo and Reeves, do they show that being a cat-zero group is not a quasi-isometric invariant?
No, they don't. Oh, sorry, you mean, sorry.
Which of these are quasi-isometric?
Right, thank you. I forgot to say it. My example of the circle bundle over the surface, right? The SL2R tilde is only differs from H2 cross R by bounded cosine 1. And so the fundamental group of that three manifold, that circle bundle over the surface, is quasi-isometric to the fundamental group of the trivial bundle. So in fact, so let me tell you. So I had this three manifold here, right, which was, so I had the fundamental group of the unit tangent bundle of the hyperbolic surface. That is quasi-isometric to the surface cross, cross a line, cross set. So that is not a cat-zero group, but it's quasi-isometric to a product of a surface and a line, which is a cat-zero group. So cat-zero groups are definitely not closed under quasi-isometry. Those are, most of these others we don't know. These classes are invariant under quasi-isometry. This one probably isn't, because you can probably screw up the regular language with the quasi-isometry, but nobody has an example. And the same here.
Do you have like stability properties that for semi-hyperbolic groups if you consider a good class of groups?
That's a very good question, right? So yes, you want combination theorems that say if I combine them with natural group operations, for example, as graphs of groups, then you stay in the class. Now, for hyperbolic groups, there's the Vespina-Fein combination theorem, basically. For all of these classes of groups, if you do something simple like take a direct product or a free product, you're fine. Right? So free products, all of these classes of groups are closed. You take two groups in class, and you amalgamate them, so you just smash them together, that will stay in the class. If you amalgamate them on a finite subgroup, you'll stay in the class. You can then cook up more general theorems, but they tend to not be very satisfactory. And there's a good reason for it. You have to be careful. If you're looking back at the literature of the time, there are various false statements about what sort of amalgams you can do. There are also true statements about what amalgams you can do. And Eckstein and Thurston used some of those true statements to prove their theorem about three manifolds. But let me give you a bit of a warning. See, if somebody writes down a theorem that says something like, these are nice groups, and this is quasi-isometrically embedded in here, then you stay in the class. That's the sort of theory you'd expect, right? So in the classical world, they've got a non-positive curve space X, and you've got a non-positive curve space Y, and you've got some Z, which is embedded by a local isometry in both, and you glue them together, and you've got another non-positive curve space, right? As long as this is totally geodesic in both. When you quasify that, you expect this to be quasi-isometrically embedded, or something a bit better, something called quasi-convex on both sides. You glue them, you hope to stay in the class. And hyperbolic groups are a bit like that, as long as you avoid some obvious pathologies. But this isn't true in general. Let me give you a very easy example. You can take z squared and amalgamate it along with another copy of z squared along a subgroup that has index 2 in both sides. So that, if there's any sort of easy gluing theorem, this should be it, right? Easiest possible thing you can think of is a cat-zero group glued along something that's just index 2. Now that C, since it's got index 2 on both sides, is going to be normal, which means if I factor it out, what will I get? I'll get a Z mod 2's got a definition of equal to. and you're not quite sure how this acts on this. Right, this is obviously this way. You can cook up examples like this. You can twist these embeddings so that this is actually a lattice in Sol. So it's a group that's a lattice in a Lie group Sol. It has exponential isoperimetric inequality. It can't act on any space, nicely on any space with non-positive curvature. Okay, you can cook this up. So you sit inside here as a subgroup index 2, you have Z, and you split that, which means that Z has a subgroup index 2, which is some sort of porous bundle over a circle. But you can make it, for example, so that that polynomial is a hyperbolic polynomial. And then that's a lattice in Sol, and that's not a non-positive curve group. Okay, so it's actually, you have to be very careful with combination theorems. But you can do it, but even